Today, chapter 30, Thursday, chapter 31, and we're done. It turns out, though, as I was sort of re-preparing for today's lecture, I realized that a lot of the things I prepared, we're not covering in this class. If you look at the syllabus, we only go through section 5 in chapter 30, which means that, well, there's not really a whole lot in chapter 30 we have to cover. In fact, if you look at the slides, the first 6 slides of this chapter are the first 5 sections. So all that other stuff that's hanging out there, we're not going to do, which means today's class might be a little on the shorter side. Just because there's not much in there to do. If we do the whole chapter, we would need a couple of full classes and some of the things get a little involved. But for whatever reason, I don't know, maybe the physics department decided you get those in another class. I'm not really sure, but we don't cover them in here. So instead of just going through those slides and telling you it's not going to be on the exam, and then you not listening or leaving, I'll just not cover them. That seem all right? Yeah? Okay. And then chapter 31, I think we only do the first 3 sections, which is kind of extra short. Although there's some kind of heavy stuff in those first 3 sections. We'll have to see how long that takes on Thursday. So we've got 6 slides to do. I'm probably going to add one blank one because I've got a bit of a derivation that's going to take some space, and I'm going to subtract one of them. So it's still actually going to be 6 slides, all right? So the first part of chapter 30 involves a continuation of Faraday's law in a way. This whole idea of changing magnetic flux, doing things, and inducing a current, as well as a variety of other things in a nearby section of wire. So we can extend this idea to a case where I have 2 coils of wire that are sitting relatively nearby each other. If I have a changing current in the first coil, well, that's going to create a changing magnetic flux both through it and the nearby coil, and will end up inducing a current and also, of course, a potential difference in that second coil. So here's what we're going to do. We're going to say that the magnetic flux through 2 as a result of coil 1, and I'm writing that with the subscript B for now. As I keep going, I'm probably going to drop that because it just gets a little subscript heavy, and I don't think any of us want that. Just keep in mind it's the magnetic flux, and I need to keep in mind also that there are multiple loops, so maybe we should put in front of that also an N2. So the total amount of magnetic flux through coil 2 is the number of loops times the magnetic flux through that particular coil of wire. It is going to be directly proportional to the current that's in coil 1. And since it's directly proportional, there's going to be a constant of proportionality out front, which has a name, and I'm going to give it the same subscript 2-1. This thing is known as mutual inductance. Mutual inductance is a factor related to both coils. So both of them could have different geometries, number of loops. That constant is based on the construction and the geometry of the 2 coils. It's not based on how much current is in the first loop. Much like when we had capacitance, we had a value for capacitance which didn't depend on the voltage or the amount of charge. Rather, it was about the physical construction and physical characteristics of the capacitor itself. This is analogous in a lot of ways to that. So we're going to take this and plug it into Faraday's law. And it's going to help us find how much induced potential we get in the second coil. So let's focus still on coil 2. So the EMF in coil 2 that's induced is going to be equal to negative N2 times the rate of change of that magnetic flux, so flux sub 2-1. And let's solve this thing for flux 2-1, and then we're going to plug it in there. Okay, so M21 I1 over N2. So at that point, we're going to have minus N2 times the derivative with respect to time of, let's see, M21 I1 over N2. And some stuff cancels out, and some stuff is constant, and we quickly see that it's going to be about how quick the current is changing. So the N2s are gone. The M21 is a constant And then I just have negative M21 times the rate of change of current 1 gives me the potential difference that's induced in coil 2. So in a way, it's kind of exactly what you would expect. A changing current in the first coil is what's causing the EMF. Well, we have a term in there for the changing current. Also, the construction of the two coils, their proximity, how big they are, the number of coils, we have a factor for that, which is known as the mutual inductance. And it turns out we could do this the exact other way. It works both directions. So if we had focused on a changing current in coil 2 and just flipped all the subscripts, all of this works perfectly in reverse. In fact, it turns out we could also write that the EMF in 1 is equal to minus M12 times the rate of change of the second current. And really, it turns out that M21 is equal to M12, and we might as well just call that M for this certain pair of coils of wire, because it's based on both. I should point out that this thing known as mutual inductance, it has a new unit, and I think it's my favorite unit of the entire class. I'm not sure why. I'll just tell you about the unit, and maybe by the time I'm done, you'll be like, oh, I can kind of see why that's his favorite. I don't know. The unit is the Henry, which is just abbreviated H, of course. I think it's because, like, often the inductance values aren't measured in multiple Henrys, but it's typically small. So we may have micro Henrys or milli Henrys, and that just makes me think of just like little dudes. I don't know, like micro Henrys. I don't know. It's amusing for no other reason than that, I guess. All right. So a couple of applications. If you have a pacemaker, anybody with a pacemaker? You don't have to answer that question. Maybe you do. Maybe you don't. I don't think I have one unless someone did surgery when I was asleep or something. It needs power, right? At some point in the past, perhaps, maybe surgery would have to be done to replace the battery. That's a terrible, horrible thing. So instead, we could use a setup like this where there's a coil in the pacemaker itself, and we can position another coil nearby on the skin, such as they're in relative close proximity, and we can induce a potential difference in the pacemaker and supply it with some power or recharge a battery that's in there without having to do surgery. So that's kind of nice. But also, I should have dug this out before we got started. Let's see if I have it in here somewhere. I think I do. Ooh. Well, why don't we just decide to quit completely? I bet that means the remote's in there somewhere, don't you think? I thought so. Let's see. Where's the thing I want to show you? This bag's too big and too deep, and I have too many charging cables and things. Here's what I'm looking for. No input. Aha. Anybody got one of these at home? For your phone? No. Yeah, wireless charger. Take it apart. There's a coil of wire in here. Take your iPhone 8 or above, I think, and a variety of Android phones. There's a coil in there that's positioned on the battery. Put them in proximity, wireless charging. Now, I see a few of you shaking your head. You're like, those things seem stupid. They're not stupid. First of all, Faraday's law. You got to love Faraday's law. You get to use Faraday's law every day. But also, there's just something about being like, you're like, it's like night. You want to go to sleep. And there's that wire that you want to plug your phone in, and it's like made its way under your bed somewhere. And then you're like, I'm sleepy or drunk. I'm not sure which, right? And you're like, and then maybe you just throw your phone aside and say, forget it, I'm not going to charge it, right? Now, that doesn't seem like a terribly bad thing, but isn't it just a little bit nicer to just say like, my phone is charging, fantastic. Yeah? It seems like a small luxury in life, but there's something about it. You charge your phone so often, it gets kind of nice. Yeah? The efficiency is definitely lower than if I plug in a cable. Is it terribly lossy? Not really. Like the charging rate, it doesn't compare to fast charging, which is available on some phones, but it's still pretty decent. As you separate, the efficiency, of course, drops radically. All right? Let's see. I wish I had wireless chargers everywhere. I've got one in my car. Got a couple in the house. Yeah. Anybody else on the wireless charging bandwagon? Just one person? Two? For your toothbrush. I like it. A variety of things have wireless chargers, and I think everything should. I look forward to a day where it's like I don't know, the wireless charging goes to another level, which involves other technologies that are being worked on, where we just walk into a building and all of our stuff just goes bloody, 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 and starts charging. Maybe one of these years or decades. Things like this are presented pretty often at conferences, but it's like commercial viability so far really hasn't worked out. You might wonder, like, are there issues with just beaming power everywhere through a building? I don't know. Lots of studies must be done, but who knows, all right? That's all I want to say about mutual inductance. Let's see if I can get the screen working again and hope that I don't inadvertently push the remote, which is apparently hiding in my bag somewhere. It says it's there, but alas, it's not. There we go, all right? So we've got a pacemaker, and also just regular old wireless charging is using this technology. All right. In addition, it turns out that we get a similar effect even if I have a single coil of wire. Your question first. Instead of total flux, where? You're talking about here? Simply, if I understand your question, simply because we were looking at it from one coil's perspective as opposed to looking at both of them. One is being treated as what's generating the flux, and the other is receiving it, instead of it going bidirectional. Okay? Anybody else? Yeah. Some. Just like we had back EMF before, there's always a little bit of a reverse effect, but we're going to ignore that for all purposes in here. Anyone else? That's one slide out of 6. Yeah, I feel like I need to talk slower. It turns out a couple of these slides take a long time to explain. So if I have one coil of wire all by itself, and it has a current through it that's changing, it turns out that that single coil of wire also experiences a Faraday's and Lenz's law effect. In essence, it's like the single coil of wire just doesn't like changes. It's happy to accept whatever's there, but as soon as I make a change, it sets up a back EMF, you might say, to try to oppose what's happening. We can, for a single coil of wire, which we see illustrated here, use basically the exact same equation. It's just we don't have all the subscripts this time, and we're going to change the symbol we use for not mutual inductance this time, but for just regular inductance. So this is the rate of change of current that's passing through that single coil of wire. It's going to produce an induced EMF, and it is proportional to the change of current. And it turns out that this thing is just known as, well, inductance. It's also in Henry's. Which leads us to a new electrical device, or a new circuit device, which is the inductor. If I have a coil of wire that experimentally determined produces enough of an inductance effect, we can call that little coil of wire an inductor. But once again, this is not something magical. It's literally just regular wire that's been shaped into this coil shape, much like a capacitor. It was just regular conductors positioned near each other. Okay? Because it's taking the shape, and Lenz's and Faraday's laws are taking effect, we end up with some interesting things that happen. So, first of all, take a look at the case A up here on the top left. Notice the switch is open. Nothing is happening. We have an inductor. We have a resistor. If I then close the switch in the diagram below, well, you can imagine that DC source is immediately going to say, like, ooh, send current. The inductor says, no, thank you. Like, immediately tries to repel that as much as it can. But again, since it's just a coil of wire, it has no magic powers. It's going to lose, and it loses immediately. The only thing that it can really do is sort of delay the inevitable. So it's going to set up an induced magnetic field in what would essentially be a backwards EMF to try to oppose that current growth. But if I wait long enough, essentially it just turns into what it is, and it's just wire that happens to be shaped another way. So after some period of time, we end up with a current that's just based on the potential difference of the battery and the resistance that's in the circuit. And according to Ohm's law, you'll end up at some maximum current. So it's just delaying what's going to happen. We are going to focus a little bit more on this particular circuit in a couple of slides. Okay? We're going to deal with the details of that process and how it happens. But before we do that, there is an aside. So let's just call this what it is. It feels like it's disconnected in some ways, and for whatever reason, it's in our textbook at this point. So it seems like as good a point as any to deal with it. You might remember that we had several equations, it turns out, for how much energy is stored in a capacitor. One of those was U is equal to 1/2 CV squared. We also had energy density in an electric field, which could be between the two plates of a capacitor, the same sort of idea. And I'm just going to put those two equations up there just so you can see as we work through magnetic fields and inductors and get some similar equations, you can kind of see how they compare. In this particular case, the energy density little u was equal to, 1/2 epsilon naught E squared. So I want to find two equations that are just like these, except related to an inductor and the magnetic field that's inside the coil of the inductor. How much energy is stored by this particular device? So let's start with the equation we had on the previous slide. The induced EMF in the inductor as a result of the changing current through that coil of wire. And you might remember also that power is equal to the current times the potential difference. And I'm just going to use the absolute value of the potential difference and plug it in there. So now we've got power is IL di dt. And again, we're focused on what's happening in the inductor and in the magnetic field in that inductor. Also, power can be written as a energy divided by time, and since energy has the exact same units as work, we could express that as work over time. So rearranging that, we could say that work is power times time, or we could write it in a differential form as dW is P dt. And we're going to use all of this together to find the amount of work to raise the current from 0 to just some value I. Clearly, we're having to fight against the inductor. I can't just turn the current on and it's just there. I have to fight against this effect that's happening from the inductor to get the current up to some level. Essentially, by doing that work, I'm putting energy into the system, and energy is now going to be stored by the inductor. So let's find how much work is required to do this particular process. So we'll say that work is going to be the integral of dW from above, which is going to be the integral of P dt, and then we'll take that power equation from above and plug it in. So this is going to go, wee. Ooh. Yes, that was terrible. So let's see. I've got integral I L di dt dt. Which green do you like better? Previous or current? Current? Current. Yeah, that's awful too. You want to go with the current green? I should stick with that? Okay. I don't really care. So let's see. Those DTs are gone. And then what do we have? Let's see. The L is a constant, so then I've got I di on the inside of that. And we're going to integrate from 0 up to the current I. So that gives me, 1/2 Li squared. That's the amount of work that it takes to get the current up to that value. So I could also say that that's equal to the energy that's stored by the inductor when it's in the circuit and carrying that maximum current. You will notice, if you look right up above, that it kind of looks similar to what we had with the capacitor. It's essentially of the same form, 1/2 times a quantity that's about the physical device we're looking at. So we have L instead of C now, and instead of the potential difference across a capacitor, we have the current through an inductor. But it's analogous, and it gives us essentially the same concept. So let's take this a little further, unless there's questions about how we got there. Yeah. A permanent magnet, does it store energy? It stores energy if it can do work. So if you can conceive of a way for the magnetic field from that to do work on something else, then yeah. Okay. So we've got an equation for the energy stored. Let's see if we can find something for the energy density. And to do this, we are going to have to consider one particular case, and I'm going to use an ideal solenoid. While we're going to use the equations for a solenoid, keep in mind that you could rederive this equation using other more complicated arrangements of coils of wire, but we'll do it for this one case, and you'll see that it works for other cases as well. I'm not going to derive this equation, but the inductance for a solenoid, an ideal solenoid, is given by this. And also the magnetic field in a solenoid is given by this, which we saw in a previous chapter. So I'm going to take those two equations and plug them into what we had above. So solve this one for I. So we've got I is going to be BL over mu naught N. And we're going to plug that in right there. And then for L, we're going to plug it in there. And I will let you do that work. It turns out that now we have U is 1/2 B squared over mu naught times A times L. A is the area, the cross-sectional area of those loops or coils. L is the length of the solenoid, which means that this thing is essentially the volume enclosed by the solenoid or by the inductor. Which means I could rewrite this as 1/2 B squared over mu naught times V for volume. Don't confuse things with voltage here, or with the U, which often looks terribly similar. And we're going to take this and divide the energy by the volume, which is essentially an energy density. It's a volume energy density. And we're going to write that as little u. And then we just have 1/2 B squared over mu naught. Now we have an analogous equation for how much is stored in the magnetic field that's contained inside the solenoid. Who's got questions? Complaints? Thoughts? Anything at all? Sadly, we're not going to get to do too much with the inductor, but we can at least set it up for use in later classes. Yes? In a way, I guess. It's kind of like a variable resistor that starts at infinite resistance and goes to 0 over some period of time. Yeah. Yeah. A scrunched up solenoid. Uh-huh. When and why? Is there current passing through it while you do this? Are you okay? You? Okay, I hope so. Yeah. Good question. Kind of want to try it now. I don't know. I'm just going to leave it at that. I don't even want to speculate. It feels like it would, but I don't know. Go play in the lab or at home, in your home lab, in your lair, or whatever's happening. Any other questions? Yes, in the back. We're going to kind of look at that in just a second. It turns out that it still doesn't like change. So if I take the current away, it's going to essentially produce some current a little bit longer. So we can sort of reverse this effect, which let's just do that right now. It's the next slide. So let's look at this circuit that contains a resistor and an inductor, the RL circuit. We had the RC circuit several chapters before, and you can see that, well, this behaves in a really similar fashion. In fact, the exact same equations are used. If you just understand what an inductor is doing and how it behaves and responds to current, you can figure out which equations you're supposed to use and exactly what's going to happen. So if we were to close this switch, once again, the inductor is immediately going to say no thank you. And you get what you see on the graph below is right at the starting time, essentially no current. It quickly begins to adapt to the current and the magnetic field that's there, and it starts allowing more and more current through until it eventually reaches just the potential difference divided by the resistance according to Ohm's law. You reach some maximum current after a period of time. If, after we've allowed this to happen for some period of time, we decide like, oh, well, never mind, let's just take this and remove the battery all of a sudden. And it's like, oh, you took my current away. Like, I really enjoyed the current that was there. What are we going to do? It's going to say, like, no, current was flowing this direction. I'm going to try to keep that happening as long as I can because it's essentially a device that's just built to obey Lenz's law. It opposes the changes, which means that whatever current I start out with, it's not going to immediately drop to zero. Instead, it'll keep going in the positive, the same direction, and it'll fade away towards zero over some period of time. You ought to see that all of the stuff we're doing it's like bizarro world for capacitors. It's kind of the same thing. It's just obeying stuff with magnetic fields and change there instead of dealing with electric fields. So the equations that we had for capacitors in these circuits is basically the same as for this. We could say, first of all, during this phase, that curve is described by this. The current as a function of time is going to be I max times 1 minus e to the minus t over tau, where tau is the time constant, and it's equal to L over R, where L and R could be any combination of inductors and resistors in the circuit. I max is going to be V over R, according to Ohm's law. Once we no longer have a supplied potential difference in the circuit, the current is going to fade away, and it's just going to be whatever current you started with once you switched the battery out of the circuit times e to the minus t over tau. So you've got very similar exponential functions as what you had to the RC circuits. And I don't think there's a whole lot else to say about that. Inductors don't like change. That's the whole gist of this chapter. Okay? Let's see. Most problems that are related to this are basically just use the equations, plug in the numbers, which means there is a problem here. If you wanted to work through it later, you can. It just turns out there's not a whole lot to do. So I'm going to skip over that slide. That's the one we're getting rid of. I'm going to add another one here in just a minute because I'd like to spend some time talking about this guy. One other type of circuit that we're going to deal with in this class is the LC circuit. So now we're combining these two worlds, and it turns out there's some really interesting effects that happen. So now we've got an inductor and a capacitor in a circuit, And let me point out that this circuit is completely theoretical. We are assuming that there is no resistance. But if I have wires that are connecting the components, and I have an inductor which is just wire, there's inherently going to be some resistance. It's not perfect. This is analogous to saying, like in 7a, we had situations where we said, let's just pretend there's no friction. Same kind of idea, we could get some good results, but we knew that friction was really there and it wasn't going to behave perfectly. Same sort of idea that's happening here. If you look on the next slide, and it turns out we're not actually going to deal with this, this is where our breaking point is and what we're supposed to cover this semester, we actually include the resistance and look at how it plays an impact on the circuit. But let's focus on L and C to begin with. Notice, I want to start with the 6 steps that are going to happen, and we're starting with the configuration you see in the diagram to the right where the capacitor is fully charged when we initially close this switch. So, if I close the switch when it's in this configuration, current is going to begin to flow clockwise around the circuit. Good so far? Okay. We know that the inductor is going to oppose that and then start to allow it to happen. So if I were to look down at this graph, you can see that we're starting with the charge on the capacitor. It starts at its maximum value and it's going to start falling as it loses charge. That seems to make sense. Simultaneously, if I look at how much current is passing through the inductor, it starts by completely opposing it, and it begins to allow it to rise. So that seems to make sense from the starting point, okay? Notice step 3 there says that the maximum current will occur when the capacitor is fully discharged. So when we get to a state where it's completely neutral, all of the charge that can possibly leave this side has left, well, it sort of makes sense that once I have all the charge has left the positive side, that the current can't really go any higher. That's as high as it's going to go at any point. And you can see that that's reflected over in the graphs. Once I get to 0 charge on the capacitor, that corresponds with the maximum in the current. Everybody still good? Yeah, maybe a little bit. Okay. So now consider this case where it's like all the possible current that we're ever going to get is flowing through the inductor. The capacitor has nothing left to give, which means it's going to stop pushing charge. And the inductor says, no, this current is fantastic. Like, it's at a maximum. It's the most current the inductor has ever had in its life. And now the capacitor is going to take it away. That makes for a sad inductor, okay? Which means it's going to be like, no, thank you. I'm going to try to just keep this current going. I'm just going to keep pushing myself and fail. But what you might imagine this results in is that this is out of positive charge on this side. The inductor keeps pushing, and it's going to start pushing the positive charges now over to the other side, meaning it sort of overshoots. The capacitor doesn't just discharge, but it discharges, and now because of the inductor, begins charging the opposite direction. Okay? It's the inductor that's causing that to happen. It turns out that in step 5, since there's no resistance, it's just enough that it becomes fully charged with the opposite polarity. So I end up with positive charges on the right and negative charges on the left. And then what do you think is going to happen after that? Well, step 6, repeat in the opposite direction. So the exact same thing occurs and it becomes charged the other way. And then you end up with an oscillation, ideally. This thing would just go back and forth forever if it actually existed. All right? So this is what's known as an EM oscillator. And it is analogous to the mass spring system you studied at some point in the past. You all did do simple harmonic motion and stuff at the end of last semester, right? Yeah, you did a little bit. Okay, you at least in name covered that particular chapter. I haven't taught 7a here yet, so I'm just assuming that it happened, all right? It's the same sort of idea. If you assume there's no friction on a table and I pull back a mass that's attached to a spring, it's going to go one way, reach some maximum velocity in the middle, go the other way until it stops, and then just go back and forth between those two extreme points over and over and over again. Really, when I have it fully stretched to one side and let it go, you can think of that as being all this potential energy that's stored in the spring That's like the capacitor having all the energy stored ready to be released as soon as I close the switch. When the spring and mass get to the middle, where it's moving at the fastest, that's analogous to when the capacitor has nothing left, but the current is at a maximum, and then it charges the other way once the spring compresses all the way in the opposite direction. These situations are really identical. One is just a macroscopic system you can see. One is something microscopic that's like happening in a circuit that you can't really see unless you have a meter attached so you can make the measurements, okay? So now that I've given you maybe a feel for what's happening, we have to do a little bit of math that's related to this. Do you have any questions about the process, first of all? Yeah. Yeah, the dampening stuff we're not going to deal with. That's over on the next slide, and that's going to come into play with the resistance. If you have any resistance that's in there, then you get like those exact same curves that you saw last semester with simple harmonic motion with some kind of friction that was built in. We're not going to study it this semester, so don't worry about it. Yeah.
So for this to happen, this must happen like a crazy short amount of time, right?
Oh, yeah.
Because I feel like put a voltmeter on either side of the capacitor, see like how it's changing, it's just going to go super fast, right?
It would go really fast. You would want to use an oscilloscope instead, so you could actually track as a function of time how those quantities are changing. Okay? Yes? The sign convention for current and voltages where? As long as you're consistent, that's up to you. The only sign convention that I can think of offhand is assume a positive charge flow and base it on that. That's all I can think of offhand. Anybody else? Yeah. Mm-hmm. Yeah. Until it doesn't, and then it's going to try to keep that happening. Yeah. You would have to. It depends on at what point in the loop you're looking at it. But if you're worried about doing those equations, that's actually what I'm about to add. So I'll show you how that works out, all right? So it turns out for something like this, we can still use Kirchhoff. And we're going to apply a loop rule to this particular circuit, where I only have two things involved. That's all. So if I'm writing in terms of voltages, we could say, first of all, for the inductor, we have minus L di dt. So you could think of that as the potential difference across the inductor. And then we've got Q over C gives me the potential difference across the capacitor. And those have to add to give me 0. So let's assume we're looking at the first part of the process. We're going to say I is decreasing because the charge on the capacitor is decreasing. So we're looking at the first part of the process, which means I'm going to write I as negative dq dt. And then we're going to plug that in right over here. And this process of trying to figure out the equations that relate to the LC circuit are the last thing we do in this chapter. It's a little bit lengthy, but if you can just bear with me for a few minutes, it pays off in the end. And then when I'm done, you're like, ooh, cool, we got new equations, and I get to leave. So it's kind of fantastic. Your question? I the amount of I that's being supplied by the capacitor itself is decreasing. So the rate of change of current leaving the capacitor is falling, but I for the entire circuit is slowly rising. I would agree with that. Okay? So the rate of change of charge leaving the capacitor is what we're using here, and that's decreasing with time. So let's plug that in and take the derivative and see what happens. So I've got minus L d dt minus dq dt plus q over c equals 0. We've got a couple of positives and then a second derivative. So I've got L times the second derivative with respect to time of q plus q over c equals 0. And then let's divide through by L to get this in the form that I'd like it in. And if you remember anything from Physics 7a and your discussion of simple harmonic motion, you will see that this is the same form as the differential equation for simple harmonic motion for before. The exact same thing applies mathematically because, while it's a different system, mathematically they're identical. The exact same thing is happening. So while we're dealing with charge and inductance and things here, in the other case you'd have spring constants and masses and stuff like that. But overall, the effect is the same. The solution to this equation, Q, is Q naught cosine of omega t plus a phase angle phi. And we're going to do a few things with the solution. So the first thing that you should note is, first of all, we could say that the charge, oscillates sinusoidally. And let's hold on to that and go back to the previous slide. So Q is Q naught cosine omega t, essentially. Let me go back and let's take a look at this particular graph. Notice the graph of the charge. Well, that's a cosine function. It seems to agree exactly with the solution that we got. So now we know how the charge is varying with respect to time. It agrees both with what we would expect because of the behavior of the circuit that we were describing, and also mathematically based on the solution to the differential equation that applies to this particular case. But we could also say that, let's see, can't do that. Since I was negative dq dt, let's plug that in and see what we get for the function that describes the current. So let's see, minus d dt of q naught cosine omega t plus phi. So we're going to get I is omega q naught sine of omega t plus phi, where this thing is the maximum amount of current. So we could say I max is equal to omega times Q naught. And I'm going to rewrite that one other way in just a second. We haven't got far enough yet. So notice we have a sine function for the current. Again, if you go back to this slide and look at the bottom graph, oh, yay, sine function for the current. Everything seems to line up with the way we would expect it to be, all right? So let's go back and do a couple of other things with this, and then we will be done for this particular class. So let's take the solution. So we're going to take Q is equal to Q naught cosine omega t plus phi and plug it in to the differential equation. And see where that gets us. So we need to take a second derivative of it and then just plug it in directly for the second term. So that's going to give me minus omega squared Q naught cosine omega t plus v plus 1 over LC Q naught cosine omega t plus v equals 0. I've got a Q naught in both terms and a 0 on the other side, so those are gone. And then I'm going to factor out the cosine omega t plus phi. So now we've got minus omega squared plus 1 over LC times that cosine function equals 0. I'll take a breath and let you catch up with the writing before we pull something out of this equation. So we've got equations for how the charge is varying. We've got an equation for how the current is varying with respect to time. And plugging the charge into the differential equation leads us to one other thing. If this is going to always equal 0 for all times, that means this first multiplier has to be equal to 0. So we could say minus omega squared plus 1 over LC must be equal to 0, and we can solve that for omega. So omega squared equals 1 over LC, which means that omega is 1 over the square root of LC. And don't forget that the angular frequency is also equal to 2 pi times the regular linear frequency. Once we have this, I can take it back up here and rewrite I max one other way. So we could say that this is Q naught over the square root of LC to get it in terms of things that are actually in the circuit. Questions? Thoughts? Complaints? Okay. So that explains what we have for the first two graphs on the previous slide. You may notice there's another graph on that previous slide that relates energy. And this connects back to that discussion we had previously about how much energy is stored in the inductor and in the magnetic field in the inductor. So let's look at this one other way in terms of energy. And for energy, let's see. First of all, we could say that the energy stored in the electric field is 1/2 Q squared over C. And we can say that the energy stored in the magnetic field is 1/2 Li squared. Keep in mind we're combining our knowledge of capacitors and inductors at this point. So we're using some of the old equations together with everything that we just derived. So I'm going to plug into this first equation for the electric field and how much energy it stores, this equation for charge. So we're going to put it in right there, and then I have 1 over 2c, and there's a Q naught squared times cosine squared of omega t plus v. And for B, let's see, we have an equation for the current. So we're going to take the current equation and plug it in right there, which is going to give me, let's see, L over 2 times omega squared times Q naught squared times sine squared omega t plus v. So it makes sense that the energy that's being stored in the electric field or in the capacitor is varying with time, and the energy that's stored in the magnetic field in the inductor is varying with time. Okay, the amount of energy in each is varying because the current and the charge is changing as a function of time as well. Let's see, we can do a couple of simplifications here. So for this omega, we're going to plug in the 1 over the square root of LC. And once you do that, you can simplify this to Q naught squared over 2c times the sine squared of omega t plus v. So we've got an equation for the energy in the electric field and the energy in the magnetic field. Now, what to do with these? These are going to simplify dramatically. I need one more slide to wrap things up. So we're going to say, first of all, let's let phi equal 0, just to keep things simple. We're going to say that there is no phase difference between the two, and it's not offset from 0 at all. And also the period, you might remember, is related to the frequency by that equation. And I can also relate it to the angular frequency as well, because omega is equal to 2 pi f to help you connect all of those things together. So that means now I have the energy in the electric field is Q naught squared over 2c times the cosine squared of just omega t. And we want the times where this is at a maximum. When do I have the most energy that's in the electric field? So this part is going to be equal to 1 at t is equal to 0, and also at the period over 2, so halfway through a period, at a full period, 3/2 of a period, and so forth. You get the idea. And at those points in the cycle, that means we have UE is just equal to Q naught squared over 2C. All the energy is stored in the electric field at those points. Now, if energy is conserved, I should get the exact same amount stored in the magnetic field at different parts in the cycle. Before we do that, go back 2 slides and let's look at that particular graph. Notice in the middle, we've got a graph in red of the energy that's in the electric field. You can see it's at a peak at t equals 0. It peaks again halfway through the cycle. It peaks again after one complete period. So that agrees with the equation that we just got. All the halfway intermediate times between that should be when the inductor has all of the energy. So let's make sure that that works out. So we could say that UB is equal to Q naught squared over 2C times the sine squared of omega t. And again, this is going to be equal to 1 for t equals to basically all the intermediate points from above. So halfway in between 0 and half through the period is going to be a quarter of the way through the period. And then the next point would be 3/4 of the way through the period. And you get the idea. All of those intermediate points are going to give me a maximum in that particular energy. So UB is equal to Q naught squared over 2C, the exact same equation for these other points when all the energy is stored in the magnetic field. Okay? We got the exact same result. That is the total amount of energy that's there. It's just switching from one to the other. If you go back and look at that graph once again, they're just oscillating from one to the other. Have all the energy stored in the capacitor, it all goes to the inductor. It all goes to the capacitor, it all goes to the inductor. Just back and forth, like with the spring and mass, it was all in the spring itself, and then it was all in the mass, and then it was all in the spring, and then it was all in the mass. It's just potential and kinetic energy that are oscillating between these two things. Okay? The last thing that we're going to write, and this is it, is that total energy here must be conserved. So we could say that the total energy is equal to UE plus UB. And we could write that as 1/2 Q squared over C for the capacitor plus 1/2 Li squared. And then using these two equations from above, so this one, not those two. Which one am I using? They're on the previous slide. My bad. So we're going to plug in equations for the current and for the charge, which we had on the previous slide. And if you do that, all you get is Q naught squared over 2C times cosine squared plus sine squared. of the exact same things, and that is just 1, which means that my total energy is Q naught squared over 2C, which again is exactly what we got there. So at all points in time, that is the amount of energy that we have. It's just switching between the different components in the circuit. And that is the end of chapter 30, even though that last bit was extended. Does anybody have any questions, thoughts?